Okay, today we're going to talk about the Krebs cycle and do some comparisons to the Krebs cycle to glycolysis, think about the inputs and outputs, and think about its importance as a way to continue to burn and oxidize the carbons that are fed into our body through glycolysis. And we'll also think about the amphibolic nature of the Krebs cycle. Right? It's cyclic, and there's a bunch of molecules in that cycle, and it's really useful in that some of these biomolecules that we think of outside of this central glycolysis Krebs cycle metabolic pathway can be fed into the Krebs cycle and used to generate energy and reduced cofactors in a catabolic sense. But also there's an anabolic nature to the Krebs cycle. Some of the components in the cycle can also be siphoned off and used as carbon sources to build things like amino acids and fats and things like that. So we'll look at the different reactions of the Krebs cycle and try to lend some significance to it. We think of the Krebs cycle as 8 reactions going around in a cycle, which is different than glycolysis, where our 10 reactions were in a linear line. But before we get to those 8 reactions, we have to go through what I call anyway, reaction 0, right, where we convert our pyruvate into our acetyl-CoA molecule. We talked about this reaction 0 in the last topic, and we know that it is catalyzed by the pyruvate dehydrogenase complex, and we appreciate the complex nature of this thing. It's really complicated. It's this big machine, but we know that it does produce carbon dioxide, and it also produces an NADH reduced cofactor. So I'll try to color code some of the major inputs and outputs. And we can think of the production, especially of this carbon dioxide, as the first step in burning the carbons, combusting them. We know where the 3 carbons of pyruvate came from. They came from the 6 carbons of glucose. Now we've burned off one of them as carbon dioxide. You can think of these carbon dioxides also as totally oxidized carbons, right? Carbon with 2 double bonds to oxygen, and so it's sort of the limit of our oxidation. But as we burn the fuel, just like a regular combustion reaction, we're going to generate carbon dioxide. Okay, so now we've got acetyl-CoA, and it's these 2 carbons which originated from pyruvate, which originated from glucose, that are going to be fed into the Krebs cycle, really like coal or like any sort of fuel, and they're going to be burned off and oxidized, and the energy from those reactions are going to be harnessed primarily as reduced cofactors, like we've seen before. But let's start. So how does acetyl-CoA enter into the Krebs cycle? Well, it combines with a molecule called oxaloacetate, which may sound familiar to you because we saw it in gluconeogenesis. Oxaloacetate is really just pyruvate with carbon dioxide attached to it. And this was sort of the side step that we used to move backwards in gluconeogenesis from pyruvate back to PEP. So here's the carbon dioxide that we added to our pyruvate to give us a 4-carbon molecule. The 4 carbons of oxaloacetate are joined together with the 2 carbons of acetyl-CoA and to generate citrate, which is what this pathway is named after. Okay, so these carbons here are going to join up there. So let's see if I can figure out the structure of, let's see, citrate. Okay, so 4 carbons plus 2 carbons gives us the 6 carbons of citrate. Okay, there's no major inputs or outputs of this reaction. Citrate, oh, and what's this enzyme called, right? This enzyme is a nicely named citrate synthase. We're synthesizing citrate. Okay, now what do? Well, we just really do a recombination reaction here on our citrate to move that alcohol group down one step to form an isomer, right, of citrate, isocitrate, and this enzyme is called aconitase. In some books, you'll see sort of water coming in and water coming out, and that's true. We sort of hydroxylate this carbon and then dehydroxylate the other carbon, and so there is some water moving in and out, but there's no net production or consumption of water. Okay, now that we have isocitrate, we start really oxidizing this carbon chain, right? We've got our 6-carbon chain, and as we oxidize it, we can spit off our carbon dioxides and generate our reduced cofactors. So we're going to lose really this carbon dioxide from isocitrate. Let's see, CH2, CH2, and oxidize this hydroxyl group here to form something called alpha ketoglutarate. There it is. Okay, and we've lost a carbon dioxide, right? Burned it off. That's the second carbon dioxide if we're accounting for how many carbons we're using in our combustion reaction. And since we've oxidized this carbon chain, we've got a carbonyl group instead of a alcohol group, we're generating a NADH. I guess another thing to mention now, this is really important, I should have mentioned it at the start, is we have to remember where the Krebs cycle is occurring, especially in comparison to glycolysis. This is all in the mitochondrial matrix, and so that's going to play a big role in these reduced cofactors, because we're going to harvest the energy of those electrons in the mitochondria. And so these NADHs that we're making in reaction 0 and the Krebs cycle are in the right place to be harvested by the electron transport chain. The NADH that we made in glycolysis is out in the cytoplasm, and we're going to have to move it to the mitochondria, which is going to cost some potential energy. Okay, so we got alpha ketoglutarate here. We're going to couple this to coenzyme A to generate a molecule. Let's see if I can line this up the same way. Here's our CoA. This is called succinyl CoA. Okay, it has 4 carbons, and so here comes our last carbon. Okay, the last carbon from pyruvate is jettisoned off as an oxidized carbon dioxide here. We've also done some oxidation reaction here, and so we've generated another, NADH. Okay. Now, I've been negligent a little bit in the enzymes, but now I can make an important point, right? When we make these NADHs, we talked about this in fermentation also, these are done by dehydrogenase enzymes. And so the nomenclature of these 2 steps is pretty straightforward. This is isocitrate dehydrogenase, which I'm just going to abbreviate DH. And this enzyme is alpha ketoglutarate. I'm getting really out of space now. Dehydrogenase. It's a good key. Dehydrogenases typically are involved in the production of NADH. Okay, 1 carbon, 2 carbon, 3 carbon. Okay, succinyl-CoA goes on to produce CH2, CH2, molecule of succinate. And we get our coenzyme back here. And actually, this is a really interesting step in the reaction because it generates directly something else that we like, a GTP. And so if we're accounting for energy, we're going to keep this GTP in our pocket. It's kind of sort of a strange step where we're generating this GTP instead of reduced cofactor. I've got some thoughts about that. Okay.